Hello, everyone. Thank you so much for joining us here today. On behalf of the Kavli Institute for Theoretical Physics, it is my honor to welcome you to today's inaugural talk in the National Society of Black Physicists Innovate Seminar Series. Congratulations to our friends at NSBP for creating this compelling new forum for NSBP members to share scientific knowledge and ideas. And thank you for inviting KITP to join you as the host for this wonderful series. A quick note on today's webinar format: we will start out with a 30-minute talk followed by 15 minutes of Q&A at the end. If you have questions, please type them into the Q&A section below, and the moderators will read and present your questions to the speaker at the end of the talk. Next, I'd like to introduce you to Farah Simpson, the student representative on NSBP's board and also the leader of the NSBP Student Council. She will provide us with additional insights into the seminar series. Thank you.
Hi, everyone. On behalf of the Student Council, it is my pleasure to introduce to you the NSBP Innovate Seminar Series. This platform was created so that NSBP members would be able to share the amazing research that we're involved in, but also as a way for NSBP members and the wider scientific community to come together and engage in research together. With that, it is my pleasure to introduce to you the President of the National Society of Black Physicists, Dr. Stefan Alexander.
Thank you, Farah, and thank you, Lisa. I want to first of all, yes, extend on behalf of the National Society of Black Physicists, I want to thank the Kavli Institute for Theoretical Physics. I also want to give a special shout out. We've been engaged in some very exciting things that's really pushing NSBP with activities that really engages our members, especially our younger ones, our students, our young professional, into research activities and engagements and collaborations. And the ability for us to share our excitement for science and for physics. We've also been engaged with the support of the Simons Foundation and the Simons Observatory and the CCA with the Simons NSBP Scholars. Please look for that on our website. And today, we're having our inaugural talk, and it can't be done any better, in my humble opinion, than our guests today. The soon-to-be Dr. Delilah Gates. Delilah is completing her PhD this year at Harvard University, where she's a member for the Center for Fundamental Laws of Nature, as well as the Center for the Black Hole Initiative. And Delilah also, hails from the University of Maryland, College Park as an undergraduate, where she was a double major in mathematics and physics. And she will tell us about her current research on the theoretical and observational investigations into supermassive black holes. And so we begin with a warm welcome to soon-to-be Dr. Delilah Gates.
Thank you so much for having me. I'm very excited to share my work with you all. Let's see if I can get this done properly as far as playing this. Alrighty. As you can see from the title of my talk, I'm going to be talking about black holes. And specifically, I'm going to talk about one observational hallmark of black holes, which is the blue shift we see from the matter swirling around them and accreting onto them. This is work done in collaboration with Shahar Hadar and Alexandru Lupsaska. And thank you so much for NSBP for having me. So let's begin. So why do we care about black holes? The biggest thing is they're everywhere. Black holes, and especially very large ones, supermassive black holes, are the center of all of the galaxies, including our own and the ones we can observe in the observable universe around us. And because of that, not only are they physical, they represent a lot of different questions in different areas that we can ask. There's a lot of things to understand about the nature of matter when it's in extremely heated, like it is in the accretion disks, as well as the geometry around the black hole, as well as it presents an interesting exercise in experimental physics about how to observe these giants that are also very far away from us. Of course, as you all probably know, M87, our neighboring galaxy that's very large, has recently been imaged by the Event Horizon Telescope team, where they produced for the first time a real data image of the intensity of light from the near horizon region of a black hole. So the hallmark of viewing a black hole at these scales, of course, is things like this bright ring we get with this dark area on the inside. But of course, when we see this, it's due to a lot of the bending of light from the extreme gravity around the black hole. This isn't a physical representation. This is not what we would ever see because space-time is bent. But when we think about what we're trying to image, it's the fact that we have a black hole in some region, and around it, in what can be described as its equatorial plane, we have hot matter in an accretion disk being heated up into basically a plasma swirling onto it. So like I said, one observation that one could look for, observational signature, is this donut, this bright ring with a dark area in the center. But there are other things we might try to observe, such as the blue-shift of this light that we're getting from around the black hole, or the redshift. And as a theorist, me and my colleagues were interested in trying to describe, using general relativity, why we might see the signatures we might see in observational signatures such as the blue shift or red shift. So let me talk a little bit about why I'm mentioning blue shift and red shift and what that has to do with black holes. So we know from atomic spectroscopy that different elements, when heated, they will radiate light at fixed frequencies. Here I've shown the visible range of the iron spectrum. This is the visible light range. Of course, it has more peaks, frequencies it emits at in higher and lower than the visible range. And we also know about a phenomenon called Doppler shifting. If the emitter of light is moving away from me, the frequencies that I, as someone who's an observer, would detect from, say, iron would be redshifted. If the emitter was moving towards me, they would be blue shifted. This has relevance in astronomy because looking at the emission from stars is used to determine their makeup. It turns out stars have a lot of iron in them, and there's one particular iron line called the K alpha line at a frequency of about 6.4 keV. That's particularly interesting because since it's very prominent in stars, it's prominent in the accretion disks around black holes. And we can look at how this line is distorted for the observer to determine things about the black hole. So the iron line, which is this K alpha line, which would be one fixed frequency, is broadened because of the black hole. We have the kinematic Doppler shift. That's, of course, the fact that since the disk is swirling around us, swirling around the black hole, some of the light is being, some of the emitters are moving towards us in the disk, and some of the emitters are moving away from us in the disk. But we also have gravitational Doppler shift. So because this matter in the accretion disk is near the black hole and in a region of strong gravity, as it travels to us, there's an equivalence of having been emitted by an emitter who's traveling away from us. This is the equivalence principle that Einstein has talked about, and that you can't distinguish gravity from just being in an accelerated reference frame. There are experiments that try to detect this broadening of the K alpha line, that is the K alpha line being some of it being blue shifted as well as being red shifted, such that instead of being a sharp peak, it is now broadened for a black hole. Some of these are Newton and Suzaku, and the upcoming Athena, which will use its XIFU instrument to look at the iron line profile. We also have numeric codes that allow us to model what happens to the K alpha line. And here below, I've provided some examples of the broadening of this line for different observer angles. Observer angle 0 would mean I'm looking down at the black hole from its pole, and observer angle 90 would mean I'm in the equatorial plane looking at the disk edge on. And so there are numerical codes such as the red line by Dowser that show us that model for us the profile of the iron line that has been broadened around a black hole. And we see some interesting features. We see that for an observer at 30 degrees, the bluest part of this line that has been broadened tends to be the same for all the spin. And for higher inclinations of observation, that is closer to the equatorial plane, the bluest part of the broadened iron line, it differs with spin. And I would just like to also thank Laura Brenneman for providing us with these plots showing this data generated by the redline model. Oops, sorry, that was an extraneous slide that I didn't realize I still had in there. All right, so one thing we could ask is specifically about that edge I said of the iron line. Once we broadened it, what's the bluest part? So what is the maximum blue shift I would see from a disk? And I can ask about what it is when I view the disk from different angles. This model here, this movie here is from NASA Goddard Space Flight Center, where they show the accretion disk around a non-spinning black hole. The accretion disk is rotating, the black hole is not, viewed from different angles. One of course, the very interesting features about black holes is when you look at them edge on, the back part of the disk that's behind the black hole actually gets bent up, so you see the whole disk, even though the part of the disk is behind the black hole. So we want to talk about this maximum blue shift. We want to investigate it. So as a theorist, what do? We need to provide a simple model. So I'm going to assume, for the purposes of this investigation, that the black hole has emitters only in its equatorial disk, and that these emitters are on stable circular orbits. That means the disk will be terminated at what's called the ISCO, or the innermost stable circular orbit. So now that I have my model, I will walk you through our investigation, starting with, just for everyone's edification, a little bit about imaging black holes and black hole geometry. Then I'll specifically talk about the maximum blue shift. First, I'll go into the maximum blue shift that any observer infinitely far away from the black hole, that's on all points called the celestial sphere, would be able to see. I will call this the maximum emitted blue shift. Of course, blue shift isn't a property that is emitted. Light isn't emitted with some blue shift. Blue shift is comes from the relation between the observer and the emitter, but this is what I'm going to call the maximum emitted blue shift. And like I said, it will be the blue shift that could be received anywhere on the celestial sphere that's points infinitely far away from the black hole. This is not physical because we don't know how to surround one black hole with a bunch of detectors. We, of course, when we observe black holes, are at a fixed observer angle. So that will be the second part of this calculation, where I will ask for the maximum blue shift from the disk as seen by an observer at a particular observer angle. This I will call the maximum observable blue shift. So first, let me say a little bit about curved spacetime. We're used to thinking about special relativity, in which we have this relationship here that tells us about the distances that in space-time and how different reference frames are related, namely that the speed of light, of course, is the same in all reference frames. And so this is the invariant quantity in special relativity. I can think about writing it as having this matrix here that along the diagonals has 1 and -1, and then all the rest ones. And this object really is related to what's called the metric. The fact that this guy is diagonal and doesn't depend, for instance, on these variables tells us that we're in flat space-time, which means light travels along straight line paths. In general relativity, though, things are more complicated. This metric that describes the geometry of my space-time, the surface, if you will, the geometry of the surface on which light will travel is no longer this simple form. And basically, it encodes information about the fact that it encodes information about the fact that light no longer travels in straight lines. It travels with along the curvature of space-time. When we represent the imaging of a black hole, we can think about having an observer off the z-axis, so it makes some angle with the z-axis. We can think of the object that we're trying to, a massive object as the center of our coordinates. And then the observer will receive light from many different angles. Light, of course, will be bent around the observer due to gravity, but the observer, not knowing the particular details of the space-time, when he collects his light, he will shine it back or project it back with an apparent straight line onto a fictitious Cartesian coordinate system that's represented as a plane here. This is why, for instance, when we think of images of things being light from an object behind another lensing object, we think about things like Einstein's ring. So an object back here could send light to this observer along many different paths. We would shoot back the light as straight line projections, and what we get on our observer screen that mimics what we see, quote unquote, would be a ring on the fictitious Cartesian coordinate system alpha beta. We'll note that we're going to have our observer infinitely far away from the black hole. Of course, this isn't physical, but it is a very good approximation for the distances that we have from the black holes we observe. So let me talk to you about the geometry of a spinning black hole. Like I said earlier, in general relativity, we describe the shape of space-time by what's called the metric. This here is the metric for the Kerr geometry, or the geometry of a spinning black hole. That's the fact that, like planets, the black holes themselves are allowed to be spinning, in addition to the accretion disk around them being spinning. It has coordinates time, radius. It has an azimuthal angle, an angle off the zenith, and a polar angle, an angle in the equatorial plane. We can think of this metric as kind of describing for us the shape of the black hole that we quintessentially are used to seeing, where we say it's very flat, far away from the black hole. As I approach the black hole, space gets more and more curved. And eventually, it ends at this point that we call the event horizon. So notice that the metric depends on these parameters A and M. M is the mass of the black hole. A here is related to the angular momentum, or the rate at which the black hole is spinning. We have an event horizon, like I said. The position of the event horizon also depends on the spin of the black hole. And there's something known as the Kerr bound. This Kerr bound is a bound on how fast a black hole can be spinning. If we spin the black hole above this bound, what happens is this geometry would no longer have an event horizon. One can argue about that being unphysical because it would imply a naked singularity, or perhaps it would mean we would need a different description of space-time, but nonetheless, it's not relevant for us because if it doesn't have an event horizon, it's not a black hole. So we're going to say our black holes can be from having spin anywhere from 0 to this bound of 100% when we saturate this bound. So now let me talk to you a little bit about the behavior of photons in the Kerr geometry. As we know, we can describe the motion of particles using their momentum. This P here is the momentum of the black hole. You can think of dt, dr, d phi, and d theta as having to do with unit vectors in those different directions in our spacetime. And then we notice that the momentum depends on particular conserved quantities. Of course, it depends on the energy. This is what I denote here as omega, but omega is only an overall multiplying factor. Further, it depends on these other two parameters, the angular momentum, lambda, and a constant called the Carter constant. The Carter constant is another conserved quantity. Unlike the energy and the angular momentum, I cannot really tell you a good physical intuition of what exactly it means, but nonetheless, it's another conserved quantity. Now, given that omega, the energy, is just an overall multiplying factor, really what I can say to describe the direction of my photon in this Kerr geometry is it's really the parameterization of my momentum is described by the two quantities, angular momentum and Carter constant. In addition to the momentum, I have a constraint equation about the motion. My light is allowed to travel with. If I said to you a particle was stuck to a ring, I would have to give you an equation x squared plus y squared equals 1. Similarly, the geodesic equation tells us about the behavior of particles traveling on the surface of on the geometry of a space-time. In the Kerr geometry, one of the geodesic equations relates the angle off the zenith, that azimuthal angle I showed you before, theta, and the radius. The right-hand side, because it deals with the radius, has to do with the in and outness of my path. As I travel from my source radius to my observer radius, how far in and out closer to the black hole does the photon travel? Well, the right-hand is much more side is interesting. It tells me about what I'll call the quote-unquote swirliness. An interesting, remarkable fact about this function here is if I am to evaluate it, what I find out is it's multi-valued. So there are more than one path from a given source position to a given observer position. And what these correspond to are the number of half windings in my theta motion as I travel from my source to my observer. We denote the number by m. So for instance, here I have a black hole, an observer looking straight down at it from the pole, that is observer angle 0. And I see there's a direct path, so that's no half turnings, m equals 0. There's a path with one change with one turning, so it starts decreasing and then increasing. That's one switch, that's m equals 1. And then here, one with 2, starts increasing to decreasing, back to increasing before reaching my observer. So it's of note that there are multiple windings for light from a given source to an observer. And so now let me think about not just the way the light moves, but viewing that light. Before I told you about the apparent position on this observer screen that mimics what we see when we observe astronomical objects like black holes. And I told you that the photons in the Kerr geometry have their momentum determined by the conserved quantities lambda and eta. Well, it turns out I can simply write the angular momentum lambda and the Carter constant eta in terms of where it would appear on my observer screen, that's alpha and beta, as well as where I'm observing it from, this angle theta O for theta observer. The observer inclination, as I said before, is 0 when I'm looking straight down from the pole, and 2 pi when I'm looking from the equatorial plane. I showed you the geodesic equation that told me how I got from my source to my observer. And so in terms of the coordinates, alpha and beta on the screen time, I can solve the geodesic equation. It's a kind of messy equation, but I can get it in analytic form. So I can know for every alpha beta what source radius it came from in the geometry. But there's one more piece in that I also have to consider whether it was on a path that had 1 half turning, m, 2, 3, etc. And instead of parameterizing in m, we instead use m bar, which is related to m by the Heaviside function. And the reason for this is, in terms of m bar, we get images of each of the radii in the geometry as closed contours on our observer screen. So here I'm showing an observer, and these two images are courtesy of a recent paper by my collaborator Alex Lupsaska and Sam Gralla. And here they show for m bar equals 1, that's light that comes from the top side of the disk. M bar equals 0 is the top side of the disk, and that's direct light to the observer. M bar equals 1 is disk that was originally shot down from the disk, crosses through it a second time, and then reaches the observer. So, and here again, shot downward, then curves back up through the disk a second time before reaching the observer. And similarly, m bar equals 2 was shot up, crosses the disk once, then passes under the black hole and back up a second time before reaching the observer. Like I said, when I write my source radius as a function of my alpha and beta positions on my observer screen and m bar, which tells me which image of the disk I'm looking at, the direct image, the secondary image, the tertiary image, etc., what I see is these closed contours for the source radii. So here are plotted 3 different radii, where in purple, green, and blue, where the solid lines are their primary images, and the dashed ones here are their secondary images. That's the underside of the disk that we're seeing. And this line here, this thick red line, is what's known as the critical curve. It's the shape that these closed contours tend to as we increase m bar. As we get higher and higher images of the disk, we get closer and closer to approximating this shape. Now that I've learned this, let me tell you about how we can use it to calculate our blue shifts. So the first thing I wanted was my max blue shift to the whole celestial sphere. It's well known that if I go into the frame of my emitter on a stable circular orbit around the black hole, that it will shoot light off in many directions. Some of the light will fall into the black hole, some of it will go off to the celestial sphere to points at infinity. In this frame, I can determine that the redshift factor, that is how the redshift changes from the frame of the emitter to the observer that it reaches on infinity, will be given by this form. It's nice to see that it only depends on the source radius and its angular momentum. It does not depend on its Carter constant. That's good to know. So then we maximize over lambda, and we figure out which direction of the light emitted from our emitter, because again, lambda and eta, the angular momentum and Carter constant, parameterize the direction of my momentum. So I determine by maximizing over lambda, I can determine which direction gives me the maximal blue shift from this ring. And then I can maximize over all the different radii in the disk. Like I said, they terminate at the ISCO to find overall what is the maximum blue shift to the celestial sphere that was emitted by this disk. And for this reason, I call it GC max for celestial max. And now that before we saw that G depended on lambda and RS, but we've maximized over those 2 parameters, so now it's a function of just the spin of the black hole. All right, so this is nice. I know to the celestial sphere, I know the maximum blue shift that could have ever been received by any observer, but I'm a specific observer at a fixed angle on the celestial sphere. So for this part, now I add my observer. Of course, remember, because I'm considering a fixed observer, I have to also consider all the different images of the disk m bar. So first I start by taking my redshift that I determined before, and I write it, I plug into it my geodesic equation, that's R in terms of alpha and beta and m bar. Then I can vary over alpha and beta to just figure out for each m bar, for each image of the disk, what is the maximum blue shift I get. So I know the maximum blue shift from a given radius and a given image m bar. I can then maximize over the radii, all the radii, so I know the maximum blue shift from a given image of the whole disk. And finally, I can maximize over all the images of the disk to get the overall maximum I view from the disk from all images, from all radii. Let me mention a couple things about these quantities. Of course, like I said, there's the maximum blue shift, observable blue shift from each image, and the maximum blue shift from all images. That's just maximizing over m bar. And there's the maximum emitted to anywhere on the celestial sphere. Of course, this naturally gives me this relationship where the maximum blue shift to any point on the celestial sphere must be greater than or equal to the maximum blue shift from a specific observer angle, which again must be greater than or equal to the maximum blue shift from a specific observer angle from the m bar image of the disk. One thing that's interesting to note about the celestial maximum is I said we varied over lambda to figure out exactly what it was, and then we varied over the radius. all the radii. When I do my variation over lambda, what I can figure out is the direction that the brightest photon I get from the celestial from the disk to the celestial sphere is pointed in the direction of travel of the emitter. It's the forward direction for the emitter. Because it's emitter in this forward direction, it has no momentum outside of the equatorial plane. If it has no momentum outside of the equatorial plane, conservation of momentum suggests that bluest shifted photon must only be able to be seen by an observer who's also in the equatorial plane. So without having to think about it, I also learned that the most observable blue shift from the disk can only be observed by someone on the celestial on the equatorial plane of the celestial sphere, which again is at theta observer equals 2 pi. This is nice because then I know that when I plug in theta equals 2 pi, my celestial max and my overall max from the disk will match. But it also means that I can figure out which image of the disk M bar gave me the maximum blue shifted photon. So here's our data from oh, let me say one more thing before I do that. A nice thing about this, knowing this M bar star, the image of the disk from which we receive the most blue shifted photon, is that it helps us do this calculation. We're able to find the celestial max analytically, but the max from a given image to a fixed observer and the overall max to a fixed observer is something we have to do numerically. And the last step from going from here to here, we have to do this maximization over all images. It turns out what we learned in doing this calculation is that we can actually truncate this maximization in that if we know what M star is, which image gives us the bluest photon, we only need to consider for our maximization the images of the disk that are between 0 and M bar star. So it really also allows us to simplify our calculation by quite a lot. Great. So like I said, calculating the maximum blue shift to a fixed observer was something we did numerically, and this is our data. Let me explain to you what you're looking at. So here on this axis, I have my observer angle theta O. Again, 0 is looking down from the pole, and 90 degrees is looking from the equatorial plane. And then in different colors, I have plotted different spins. I have spins 0, 20, 40, 60, 80, 90, and 97 on my top plot here. On my bottom plot here, I have 98, 99, 99.8, which is also known as the thorn bound, and 99.9. Overlaid in black, I also have an approximation that matches very well all the curves for all these spins, which I will call low to moderate because they go from 0 to 97, as well as my high spins about 98 and above. So all the curves in this region for a low observer inclination that is close to the pole, we notice that all the curves tend to the same behavior, and there's an approximation I can make easily to determine that matches as well. And because all the curves match each other, that means these curves in this regime, this low observer angle regime, regardless of spin, are spin independent. Interestingly enough, as I move closer to the equator, I see that my spins start to stratify. And this box here is just a blow up of this box here on this plot. And what I see as I get closer to the equatorial plane is that the different spins of the black hole have stratified observable maximum blue shift, where by the time I reach the equatorial plane, they are stratified in order from smallest spin to highest spin. So 0 is here, then 20, then 40, 60, 80, 90, and 97. They don't, however, all necessarily turn over in the same order. So in this region, they're not necessarily ordered by spin, but nonetheless, we still know the shape of the curves. Additionally, I have plotted for you as dots along the axis that corresponds to an equatorial observer that's 90 degrees. As these points is my analytic calculation of what the max should be to the celestial sphere, which I said before I can deduce must only be seen by someone at the equatorial plane. This is a nice check. It tells us that our curves numerically are going to what they expect them to. Furthermore, this top row, so all my spins from 97 and down, are all have their max blue shift from the primary image of the disk. Things, however, do get weirder when I go to higher spin. At higher spin, I need to consider higher images of the disk, so the secondary, as opposed to just the primary image of the disk. So again, what I have plotted here is a blow up of this box right here. Let me tell you about what you're looking at. So in the colors red, blue, green, purple, as I said before, are the spins 98, 99, 99.8, and 99.9. What I see from the zoomed in region here is that all these curves have a sharp turn in their behavior, where and that corresponds to where they switch from having their maximum blue shifted photon be on the m bar equals 0 image, the primary image of the disk, to being on the secondary image of the disk. And even though the max is now on the m bar equals 1 image, I've continued to plot as dashed lines here the m bar equals 0 maximum to, one, show you that they are indeed smaller than the blue shift from the m bar equals 1 images, but further to show you around 98%, you can see that for an equatorial observer, the max blue shift from those two images, the primary, m bar equals 0, and the secondary image, m bar equals 1, are very close together. What that tells me is my transition between needing to consider the secondary image of the black hole to get my maximum blue shift is somewhere between 99.7 degrees, between 97% maximum spin and between 98% maximum spin. And it turns out, although even up to 99.9, I only need to consider m bar equals 1. If I go higher and higher in spin, I would need to start considering higher and higher bigger and higher m bar number images of the disk. So the last thing I'll tell you about plotted on here is this dashed orange line. This dashed orange line comes from previous work done by Alex Lusaska and friends and collaborators from the group, where they find the theoretical limit of what the maximum blue shift would be. Of course, we can't spin black holes all the way up to 100%, all the way up to max, but we know how to carefully take the limits. And when you do so, you in principle need to consider a photon that does more and more number of windings, so a photon that does quote unquote infinitely number of windings through the disk before reaching the observer. Of course, that's physically not possible, but you can still nonetheless take the limit carefully, and you can get this analytic approximation. So now, as I showed you, plotted in black, I have an analytic formula that's good for all spin for low observer inclination. We have, from previous work, a good approximation, in fact, the maximum envelope of the high spin, high observer inclination. And then it turns out in this region, where I have moderate spin and high inclination, although I do not have an analytic formula, I can subtract this off from this data my approximation that's good in the low observer angle regime that goes bad, but I can take the difference between this approximation and these curves, I can fit them with a few simple parameters, and I can get a very simple semi-analytic approximation. So now we can basically characterize for all spin and all observer angle these maximum blue shift curves analytically or semi-analytically to within 1%. Let me also tell you a little bit more about why I'm able to make such a good approximation for low observer angle, that is viewing near the pole. So I can look at the other data that goes along with finding my maximum blue shift. For instance, I can look at which radius the maximum blue shift photon came from. Turns out for low observer inclination, that is observers near the pole, the radii that gives me the bluest light is very, very big. This is good. This explains why it's spin independent. Of course, if we're far away from the black hole, the curvature of space is not quite as harsh, and we are less sensitive to exactly what the spin of the black hole is. And the other observation I can make is that from the far out, the angular momentum of the photon divided by the observer angle times the sine of the observer angle is approximately the radius from which the bluest photon was emitted plus 1, or m. This was expected, and it was described in previous work, again, by Alex Lipsaska with Sam Gralla, where what they found is that if you view a black hole from the pole, of course, the source rings you see from the black hole will be perfectly circular, and the radius of these source rings is what we call b. And what they find, to a very good approximation for both 0% all the way up to 100% spin, is that a photon emitted from radius r will appear on the screen basically at the same radii plus 1. And so that's a quite remarkable fact. And it is what helps allow us to make the nice approximations in the low observer angle regime. All right, so let me go through some conclusions. We were able to calculate the maximum blue shift emitted to anywhere on the celestial sphere. And we figured out that it could only be seen by someone in the equatorial plane. Let me skip down for a moment. Knowledge of that maximum blue shift was nice for optimizing our calculation of observable blue shift. And from doing the numerical calculation of the observable blue shift, we learned some interesting things. We learned that at fixed observer angle, for low observer angle, that is near the pole, things were spin independent. And this is because they came from large radii, and that we only need to consider the first image of the disk, the primary image. For higher observer angles, that is angles closer to the equatorial plane for viewing, spin effects became important. For low to moderate spin, up to about 97%, however, even though the source radii that gave us these bluest photons were now closer to the black hole, we still only need the primary image of the disk. However, once we go to very high spin, that is above about 98%, we need to start considering subsequent rings to get this maximum observable blue shift. And nicely, we were able to capture all these features by some simple approximations. So let me just say for a minute about some future directions. The utility of this is that we can use, of thinking about the maximum blue shift, is it can be used to constrain the parameters of black holes that we're viewing. Here I've plotted again the maximum blue shift as a density plot, where this is the spin, and this is the observer angle. And of course, right, like I said, for the low observer angle, these dotted lines, which are constant contours of constant maximum blue shift, these guys, of course, are straight lines. So really, we're only getting information about our observer angle, nothing about the spin. We can't narrow down the spin. But for higher inclinations, of course, we can start to have these contours where we can narrow down the degeneracy between which observer angles and spins could have given us a given maximum blue shift that we are able to observe. In the future, we might want to consider other models that extend beyond the ISCO. There's not necessarily, it's not necessary that astrophysically that the ISCO has to really be where the accretion disk terminates. So we might want to consider the unstable circular orbits beyond the ISCO. Remember, the ISCO is the last these stable circular orbits is the innermost stable circular orbit, but we might want to consider the unstable circular orbits or matter on inspirals. Of course, we don't necessarily expect these to give us higher, the inspirals to give us higher blue shift, for instance, but we might want to investigate it using the same kinds of methods. We could do an equivalent treatment for redshift if we wanted to. Redshift perhaps is less of a sharp feature because as before, when I showed you these broadening iron line profiles, we see that the redshift kind of dies down very gradually, while the blue shift is really a very nice sharp feature. So maybe it's less interesting, but one could apply the same treatment to the redshift. And further, one might want to try to use analytic methods and general relativity to, from an analytic standpoint, to really understand the morphology of these broadened iron line profiles. I would like to, at this point out, though, we do notice that we recovered a nice feature, right? So these are varying spin, and this 30° is a low observer angle, and really, the maximum blue shift is the same for all of them. That means, like we saw, the maximum observable blue shift for low angles doesn't tell us any information about the black hole spin. However, it is nice that for higher observer inclination that is closer to the pole, we were able to recover this behavior where looking at the spin of the black hole really was related to exactly what maximum blue shift we were able to get. Thank you so much. I'd like to, again, thank my collaborators on this project, Shahar Hadar, Alexandria Lipsaska, my advisor, Andy. Additional thanks, again, to Laura Brenneman, who was the one who used Dowser's redline code to produce for us those broadened profiles of the K-alpha iron line. And this really has been a pleasure, and thank you all so much for listening.
Wonderful. Let's thank Delilah for this awesome talk. Clap for everyone. So we're going to open it up for some questions. But we see a lot of questions here. We unfortunately are short on time, so we only have time for a few questions.
Okay, so someone asked me, is the maximum number of windings a given photon can take before is there a maximum number of windings a photon can take before reaching a given observer? And does the number of windings tend to decrease or increase the blue shift? So this is actually, like I said before, one of the major findings. Maybe I can share my screen once more. So theoretically, there isn't necessarily a limit on the number of windings a photon can make. Of course, it does get harder for a photon to make lots of windings because you can think about having where having to be aimed at infinite kind of a shrinking kind of range to load onto a geodesic that's going to wind multiple times versus one that isn't. However, does it tend to decrease the maximum blue shift? That's one of the major findings. Of course, for most ranges of spins, that spins up to 97 degrees, we see that it is, I haven't plotted for you all a higher M bar on this plot, but it is the fact that for M bar bigger than this, the maximum blue shift for these curves is indeed lower. But one of the major findings is as you push up the spin, it switches to which image has the highest, the photon with the most blue shift. So for low spin or spin that's moderate, of course, more and more windings will mean that we're going to decrease the blue shift of that photon. But as we push our spin up higher and higher, in fact, the subsequent images become more and more important as they will have bluer photons than the ones with less windings. Good question. Let me see, let me grab another one. Someone asked me if the ergosphere played a role in this calculation. Not necessarily, not explicitly. No, we didn't have to, for this calculation, we didn't have to think very carefully about any treatment having to do with the ergosphere. Someone says they're not familiar with the Carter constant. Could I talk about it a little more? Let me just say, to me, it's a weird one. Like I said, we know that in space-time we have conserved quantities like the angular momentum or the energy. Physically, as I said, the Carter constant is one that I don't really have a good physical intuition about. But it's just another one of these quantities that turns out to be conserved in the Kerr geometry. I do believe it's there more deeper explanation can be thought about it in the fact that it relates to mathematics about the type of space-time that Kerr is a subset of that have certain mathematical properties, certain space-time geometries. But other than that, unlike angular momentum and energy, the Carter constant doesn't really have one that has a good physical intuition of what I could describe to you. But just know that it's another conserved quantity. And in the case of the Kerr black hole, it's very related to the direction, the momentum of a photon.
Right. So Delilah, maybe we'll take, because we are hitting a time thing, maybe one more question, a quick question maybe, and then I'll just close out with some closing remarks. Thanks.
So someone asked me, this is a good one. You had a simulation from NASA Goddard of the disk of a black hole that was facing edge on, and I mentioned that the black hole was not spinning. And they said if it was spinning, if the black hole itself was spinning, how would the image be different? So let me just briefly say on that one, yes, as you change the, let me share my screen one more time if I can. Oops. Will I be able to do it? Great. Okay, so right, this image is nice. So what changes about the image as you increase the spin? So this is, you see how symmetric this image is? Well, and as you see how this inner area looks pretty nice and circular, what happens as you go to higher and higher spin is this side of the of these subsequent images gets more and more blunt, and instead of having a perfect circle, you have almost a more capital D-like shape, as well as the shape of this kind of gets distorted where it's no longer quite a symmetric shape, but you do indeed still see the back side of the disk above in the top half of your, and you do indeed see the part of the disk behind the black hole still when you have the black hole spinning.
Okay, wonderful. So thank you so much, Delilah, for this amazing talk and crystal clear answers. We wish you could answer more of these questions. Maybe there might be an opportunity for us to maybe have a post in the future where you might have an opportunity if you have time to answer some more of those questions. I want to just, again, thank the Kavli Institute for hosting this. Look forward to more talks to come for the NSBP Innovate Speaker Series. And again, we want to thank Delilah for giving the inaugural one. This talk will be edited down and made available. Please await to get an announcement from NSBP and the Kavli Institute for Theoretical Physics. We expect our next speaker to likely be Professor Philip Phillips, who's a condensed matter theorist, who will talk about a recent Nature paper that he published, and expect, again, in the near future, more of these talks. Thanks for joining us, and in the spirit of the Black Panther, I got to say something and share the video, something. NSBP forever. Okay. Hope everyone stays safe. Thank you.
Bye, everyone. Thank you for coming.